I'm going to be talking about electron configuration. Now, every atom has 7 principal shells, and these are annotated by n equals 1 through 7. Now, principal shells tell us about the size of the orbital and the energy of the electrons that are inside of those orbitals. Now, in principal shells, you have subshells. There are 4 different subshells: S, P, D, and F. And these look like this. S is a sphere, P look like dumbbells, D's look like double dumbbells, and F have a lot of different lobes. So every subshell has a different number of orbitals. S has 1, P has 3, D has 5, and F has 7. So the maximum amounts of electrons that each of these subshells can hold is 2 for S, 6 for P, D has 10, and F has 14. And this will all make a lot more sense when I start getting into more examples and how to actually write electron configuration. First rule is that you have to fill the lower energy orbitals before filling higher energy orbitals. The second rule is each orbital can only hold a maximum of 2 electrons. The third rule is each electron must have an opposite spin. And the fourth rule, and I'll get into this more with the examples, is for degenerate orbitals, each orbital must be filled with 1 electron before we can start pairing electrons. For this example, I'm going to start with an element like hydrogen. Hydrogen has 1 electron, and we annotate this in electron configuration with the principal shell of 1 and the s orbital, which is the lowest energy level. So we start with the lowest energy level and go to the highest. So we'd annotate this as 1 electron. Now, an easier way to look at it is with an orbital diagram. So the orbital diagram for hydrogen would look like this. This arrow is the direction of spin. So, like I had said before, every electron has to have an opposite spin. You have to annotate the way the electron's spinning in the orbital diagram. So, for the next element, for helium, helium has 2 electrons. We annotate this by saying 1s2. And we can go on to, and the orbital diagram of helium would look like this, because the electrons have to have opposite spin. Now, the next element, lithium, has 3 electrons. So 1s is already full, so we go on to the next principal energy level of 2, and we start with the lowest energy orbital, which is s, and this would be 1. So 2 plus 1 is 3, which is the number of electrons that lithium has. Now, the orbital diagram of lithium would look like this. Now, if we skip a few elements and go on to an element like oxygen, which has 8 electrons, now we need to go to the 2p, and the p orbitals have maximum electrons of 6, so these 2 would be full, and the p would have 4 electrons. And the way you annotate this in orbital diagram so this is where the fourth rule for the degenerate orbitals comes into play. When you add 4 electrons into the p orbitals, you can't add them both together. Every p orbital has to have at least one electron before we can start pairing them. So you start by filling in the p orbitals with 1, and then you would add your 4th. About some shortcuts with the periodic table to find your electron configuration. So the periods here on the side are the same as the principal shell number for the elements in that period, except for the d orbitals, which will be the period minus 1. Group 1a and 2a will end in the s orbital. The transition elements will be the d orbitals, and the group 3a through 8a will be the p orbitals. So, as an example, we can start with an element like phosphorus, which has 15 electrons. So, phosphorus is in period 3, group 5a. So, phosphorus is going to end in 3p. So to find these the beginning of the electron configuration so that you can get in its hole, you start with the beginning of the periodic table and you fill it in. So 1s, 2, 2s, 2, 2p6, 2s, 2. And then, when you get to 3p, you'll need 3 more electrons. So, in order to check this, you can count the electrons, and if they add up to 15, you got it right.